electron here goes, it can never be in here. It won't ever be in there. Even if I make it go up there, it's never in between. So this is really like if you're driving your car going 40 and now you're going 50, but you never went 45. That sounds wrong. That's actually correct. That's how it works. But because of that, they're only going to absorb and emit discrete energies. And whenever you see color, you see light coming out of something, or you see, the color of things, paints, usually there's an electron involved, because the way you get these things to jump around is you use light. So if I have an electron here, and then I'm going to bring in light, we call that photon. So here comes the photon, and it makes the electron jump. So this is, quantum leap. So that happens. And again, it's not in between there. It just goes up to there. That's absorbance. And it's only going to absorb that light. It's only going to absorb that photon if the energy matches perfect. Otherwise, nothing's going to happen. Even if the energy is too much. Even if I have more energy than I need, it's not going to happen. It has to be exact. And some of that has to do with how photons act too. So it can only do that. Now I have this electron up here. And usually things won't hang around up here. Same as if you put a ball at the top of the hill, it's going to roll down. So it falls down and light comes back out. So when you see emission, you see light coming at you, it's because an electron relaxed and then that energy comes out as light. And now I see light, like all the lamps. So this wavelength, this energy, it matches that energy difference. Okay, so when you're designing materials, part of this is about getting the colors that you want. And again, when you see light coming out or into something, it has to do with these energy levels. And here's the electromagnetic spectrum. And we usually characterize light by the wavelength. So short wave, like 350, blue is around 400, green's like 5 something, red is 600. Infrared is getting out here, like heat energy. UV is down there, and I've got this thing VUV, that's vacuum ultraviolet. That's where I tend to play, is in the VUV. And we can make all these kind of different colors. And when you design devices, part of it is about getting those colors out. And how do you get those out? Usually you make something called a phosphor. So you're going to make a material that emits the color of light that you want. And I'll show, I've got my super janky display over here. We'll do that in a second. So what I actually play with are what are called phosphors. These are solid state luminescent materials. These are materials that will absorb energy and turn it into light. And usually we want visible light. If we're making a display, if we're making a lamp, we want it to be visible. Sometimes you might want UV or infrared or other stuff. But it's all about designing the material that does the tricks that you want. And often how you do that is you make a doped material. So here's my model for how we write this down. I'll write yttrium oxide and then put a colon and then put europium. So what this means is there's a host. So most of this crystal is just yttriums and oxygens. So yttrium, oxygen. Then once in a while you substitute. So I'm going to put europium in here for some of that. So maybe you do this 10% or something. So 10% of the yttrium atoms are europium now. And the host is really just kind of holding that atom there so that it can do what you want, which is really generate red light in this case. So this is what I spent a lot of my world. So I started getting into this working with Doug Kessler. He was more into synthesis and some other things. And he's like, oh, you're kind of a PChem guy. You should look at phosphors. And I didn't know what that meant. And then he showed me excitation spectra, and I really didn't know what that was. but I was like doing this. Yeah, for sure. What in the heck is that? And I'll show a little bit of that kind of data. So this is a phosphor, usually a host. Most of the atoms are this thing, and then I'm going to put some other stuff in there. So when you make phosphors, a lot of times you want red, green, and blue. Why do you want red, green, and blue? Because your eye will pretty much take this and make all the colors. I think I'll show you that now. But here's a bunch of different phosphors. So here's some examples of red phosphors. Europium-3 is pretty common. Some green phosphors, some blue ones. I'll talk about that blue one a bit. This is the old CRT phosphor. For those of us who remember cathode ray tubes, the heaviest invention of mankind. At least Tony had the heaviest TV. I didn't. Yeah, some of us carried that TV a couple times. Okay, I'm going to try to show you this. We'll see how this goes. So I've got red, green, and blue. So I just took phosphor out of the lab, and I put red, green, and blue in the corners. and then I mixed them together. I think you'll be able to see this okay. So here's green, blue, red, and then all I did was mix different amounts together. So like I can get yellow and orange and stuff just by how much red and green emission I get. Or I can do these, whatever, these are the fancy crayons. Teal or whatever, seafoam. Then here's some purple stuff, and then that one right there, that's the white point. That's just those three together. So even though there's actually colors missing, I'll show this in a second, your eye will just say red, green, and blue. And so when you make a lamp, you mix them together and you make white. When you make a display, you separate those pixels so that you can pick the color that you're going to make. You can make any color you want that way. So you'll put pixels in there, I'll show that too. I have water, but I feel like I should be drinking whatever's in this bag. But I have not opened it yet. Okay, so I got to explain a couple things here. One is about this. So as phosphorus scientists, we have to do a little bit better than saying, dude, that's green. So we characterize these things using something called an emission spectrum. So the visible spectrum is between about 400 and 700 nanometers wavelength of light. And so if you have something like that, what you need to do is actually measure the light that comes out. And so this is an emission spectrum of a red phosphor. And you get a bunch of peaks. This has to do with the energies of all the electrons. You get this big peak at 610, that's red. So red phosphors have emission spectra that look like this, they make red. Green, around 550, that's where your eye sees it. So here's some green emission. Blue, those emit light around 450. So what you do is you hit the sample with some kind of energy. There's a lot of different ways to choose the energy you hit it with. And then light comes out, and you can take these emission spectra. And then when you make a lamp, you want all three colors. So maybe you do something like this. You mix the red, green, and blue. This is the actual emission spectrum of a fluorescent lamp. So actually those two lines are from the mercury in there, because this thing, the excitation source inside the lamp is a little bit of mercury vapor. And when you turn on the switch, it generates a bunch of ultraviolet emission. That excites all those phosphors, they emit, they're all mixed together. Your eye says it's white. But this is really what's coming out. And it's kind of cool because there's a bunch of stuff missing. Like if you look at a spectrum of, like the sun, or like a filament bulb, like the old school filament bulbs, the filament bulb works because you get the wire crazy hot until it emits white light. Then if you look at the spectrum, it's just all the wavelengths. These tricolor lamps just have these three. And you're like straight missing some colors, but your eye just fills it in. And you can make anything you want by doing this. But okay, this is emitting 254. So the other piece of this is finding materials that are going to work if I hit them with that energy. And so this is the emission side. This is the light that's coming out, but I also have to worry about what's going in. And that's called an excitation spectrum, and this is much more confusing. So what you do is, you look at, so here's yttrium borate with europium. Tracy probably collected 5 million of these when she was doing work. Actually, we worked with this so much, so many people have made this and measured this. So you look at the emissions. So I'm going to pick that peak there. Oh, I have a pointer. Oh yeah, here we go. Here, we're going to pick that peak. And then what we do is we sweep the wavelengths we're hitting it with. So you see this is a lot shorter. This is 230. So this is all ultraviolet, or even what we call vacuum ultraviolet, really short wavelengths. And I see what wavelengths in are going to make that emission. So the y-axis is kind of weird. It's actually the intensity of that emission when I hit it at this wavelength. So if you look at this material, it's pretty lame at 250. It's not very good. So this isn't in the fluorescent lamps. Those are all exciting at 250. This is no good. But plasma displays worked over here, like 150. And this, if I hit this at 150, I see a lot of this light. So this is called an excitation spectrum. This is a big part of the kind of measurements that we did, was looking at, okay, because this tells you a couple things. First of all, where is it going to light up? But also you can start digging into the weeds about what's causing these different excitation events. And that's what a lot of the time we spent doing. So here's how a plasma display works. And this is really how I got into this. Was at Sylvania. It was very cool. At the time, plasma displays were very hot. And I got to be the lead on the red, green, and blue for plasma display. It was awesome. They had tons of resources. It was kind of fun. It was pretty young. I was like 29 or something, and there was like all these old timers, and some of them weren't ready to embrace me. But you know, it kind of works like this. Okay, I'm gonna make these channels. I separate the red, green, and blue now, and then the signal comes in and tells me how much at each pixel. But here's really much shorter, 147. So this is a lot higher energy, and really the processes going on in here become a lot different, which is kind of where I went down the rabbit hole for a lot of my career. Then you make these sweet plasma displays, which when they were first coming out, they were like $20,000, and they were selling them at like a major deficit at a loss because they thought they were going to make all their money back. Because we all said this: no way are you making a big liquid crystal display. For real, everyone I met with, yeah, just can't make them big, dude. So these people were wrong. And I think I want a home that's like 55 inches or something. So that was mistaken. But for a long time, up until about 04, 06, tons of research on how to make these work. But these excite at this shorter wavelength, and that's really where I went down the rabbit hole. Here's really the difference. If I excited a lower energy, let's say this is low UV, when I excited a wavelength like this, the host is really just kind of holding that atom there. And then the UV comes in, it hits the europium makes light. And this is real well understood. Okay, but if I go to higher energies, then what happens is I actually excite electrons in the host. The host stops it. Then this energy has to get over here somehow. We know it does because we still see that light coming out. But now there's this mystery step here. And this plasma displays used to do this. X-ray works like this, other scintillators, high energy particle detectors. When the energies get really high, this isn't really in play anymore. Now the host is stopping that thing. And when I was at Sylvania, I was like, well, this seems like an important step. Like, what makes this efficient or not? And the answer was, I don't know, but you better have product by next Friday. Pretty much how it was there. It's like, can I have 2 weeks since nobody understands it? And so it really is this part. This is the question mark, and there wasn't a lot known about that, and that's where I got down that rabbit hole. So I'm just going to tell a couple stories. There's so many stories to tell. I picked a couple. And like any great saga, mine begins with episode 4. The blue phosphor problem. This doesn't look like this actually when I did this upstairs, but okay. Hopefully I don't end up in a death match with this thing. Anyway, episode 4, the blue phosphor problem. So this was started when I was at Sylvania, and I kept working on it when I came here. The blue phosphor is interesting because it works in fluorescent lamps and in plasma display. It's pretty much the only material that does. But when you put it in a plasma display, the energies are really high and it damages the phosphor. And what happens is over time, the color goes down, and you build your display, you're expecting a certain amount of red, green, and blue. You can make all the colors. But if the blue starts to do this, then all your colors are off. Also, you get burn-in. So like, oh, I left my PlayStation on overnight, and now the PlayStation menu is burned into my TV. So I know some of you know exactly what I'm talking about. So this was, when I was at Sylvania, we were working on this really hard. And then marketing people would say things like, oh, just get a different one. Okay. Where do I go for that? Because there isn't a different one. So everyone was working on this, trying to figure out why is it degrading and what can we do about it. And when I left Sylvania, I signed a research agreement with them, so when I came here, it was kind of cool. They just gave me money. And I used it to buy some stuff and to work on the blue phosphor problem. So here's what I'm talking about. You just put it in the TV, it looks like this. Then you keep bashing it with vacuum ultraviolet, which is at 150. And the brightness goes way down, and you see that the shape of the peak is also different, so the color's not the same. So this is what was happening. And they started sending me all kinds of samples, and we were working together back and forth. It was really cool. Right before I left, I helped build this gizmo to do the damage. So this was the problem that we were trying to solve. Okay, so I got to talk about this blue phosphor. So here's the emission. That's the blue light that you see. So again, here's the excitation spectrum, and we only collected here, but it pretty much does that. So when you excite this is why this works at both wavelengths, lamp and plasma. So here's around 250, you get a lot of light out at 250. You also get a lot of light out at 150, that's plasma. So this was good for both. But this is really important here. So this piece here is if I'm just hitting it directly at the europium. This is if I'm going through the host. And this is what's happening in a plasma display as you're going through the host. So we made kind of a crazy discovery. We were doing all kinds of experiments. It was cool, it's me and a couple undergrads splashing around the pool, trying to figure out what's going on. And we made this rather crazy discovery that if I don't put europium in, I just put this by itself, it emits a bunch of light in the UV. So this is like 250. So this is no dopant. So you hit the blue phosphor, hit it at these wavelengths, including 150, which is the plasma wavelength. And even if there's nothing in there, you get all this UV emission. This is pretty unusual actually for oxides at room temperature. This is almost never happens. We were trying to do reflectance measurements and it was acting just really weird. The data were really weird. And I finally said, it's acting like it's emitting light. So we took everything apart, we reconfigured our instrument so we could measure down here, and then we said, whoa, look at all this light coming off. So here's the thing. Here's the excitation spectrum for the blue. So again, the purple stuff is what the host does. The blue one is if you just excite, so this is 300, so 450 is out here. So if I look at what causes that blue emission, when it's doped, when europium's in there, I can hit the host, I see blue light, and then I can hit, this stuff here is hitting europium directly. But you see it overlaps perfectly with the light coming out of the host. So that implies that this light that's coming out of the host is being used to light up the europium, which is pretty unusual actually. I've not really seen examples at this magnitude. And it was a little bit one of those kind of dumb luck things where you're just working on stuff and then you see something weird and you try to figure it out and it turns out it's the key to the whole puzzle. And that was this. So here's more proof that the europium is absorbing that light. Because if I have so undoped, we call this BAM. If it's undoped, I see this much light coming out of the host, and I start to put europium in, it pretty much goes away, and it all goes to the europium. And we did some other experiments to kind of show this is what was happening. Because if you just look now, just without the europium, and you damage the host, this thing goes away. It goes way down. And this is being used to light up the europium. So actually damaging the phosphor is really damaging this host. And what we figured out actually is that you make something called a color center. So you make something that's basically a light trap, and it absorbs the light and dumps it as heat, and you don't get any photons out. So the undoped host emits all this light that goes away when we put this in there, when we damage it. So it kind of works like this. Okay, there's my phosphor. In this case, the photon gets excited in the host, then it emits light. If it's fresh phosphor, this emits light, it excites europium, light comes out. But if we damage it, then what happens is this should be happening, and instead we block it. So we get color centers here, and those block that emission. This was pretty wild because I had this group of students, like I said, some really good students. One of whom surprised me and is here today, several of them actually. But we were messing with this and figured out what's causing the problem. Part of our answer to this was also, this is a fundamental property of the material, so sorry, you can't fix it. But I did learn later that a lot of researchers were reading these papers. We published two that were very cool. This I did with Brandon, who was an undergrad here early on in my career. He was a really good student. So Brandon and I published this paper talking about the host lattice emission and how this worked. And then another group of students, Greg was at Sylvania, but then we went through and we kind of explained this whole thing about all that absorption. We did some other experiments. Morgan's here, which is cool. I didn't know Morgan was coming. I expect I'll see Brendan at some point. He's probably gonna help me drink beers later. So these two papers got cited like almost 200 times, and Todd said I was famous in Japan. It's kind of a joke, but it's kind of true actually, because most of the work on this was being done in Japan. And this got out and everyone started working on this and realized that this was connected to the problem. So that was very cool. I got invited to do some talks and some other stuff. And that was sort of the blue phosphor story. And that was very cool work, and also just really excited to do this with just some undergrads in the lab. And then we solved this problem that no one had figured out. Okay, on to episode 8. The transfer efficiency problem. That's too bad this looks so pretty upstairs. It's just better font. So here's the transfer efficiency problem. I excite this thing, so in that blue phosphor, the host is emitting all this UV light. That's not usually what happens. Usually what happens is I create this excited electron in the host, and we call this an electron-hole pair. They follow each other around, and this acts like a positively charged particle, even though it's a hole. It's like where the dirt used to be. But in this case, it's where the electron used to be. So this is the energy now. I've created this excited electron, and it can do all this stuff. And again, a lot of the stuff is hiding. All you can really measure is what did I put in and what came out. So when I started going down, what sort of my research career became about was really this. There were theoretical models to describe all this stuff. No one had measured this. So can we do experiments to get data that can support these models? Can we figure out what makes one material good at this and another material terrible at it? And the ultimate thing would be really cool is if we could predict the material, the efficiency before we do anything. Can I just look at the formula or the structure or something and say, oh, I know what that's going to do? Not there yet. But that was the big picture goal. This is definitely what you put in a grant. I'm just going to be able to predict everything if you give me this money. So that was what we got obsessed with. So this is a hidden step in here. And this transfer efficiency, which is how many of these make it over there. This notation eta sub t, this is, someone started this and everyone else said, okay, you call it something, we're going to call it that. Transfer efficiency. Here's the issue. I put in 100, say I make 100 of these. And then I say, oh, 60 came out. The rest of them are all going other places. So maybe 5 go to the surface. Usually, if the particles are big, you don't see much of that. But I'll talk a little bit about that. Maybe 25 get killed by stuff. This could be defects, could be impurities, whatever. And then what's really confounding is that even if, say, 70 of them get over here, this is probably not going to emit 70. This is something called quantum efficiency. This dopant, not every one of them is going to give you light. You lose some of that energy as heat no matter what. So you can't just say 60 out, oh, 60 got to the europium. Because really you don't know, because there's another step in here. So you can measure in, out, and you're kind of not sure what the rest of this is. So we did a bunch of work. I spent a whole summer basically reading papers and trying to figure out how can we measure it, what's it supposed to act like. And we came up with a way to calculate this, and I'm not going to get into the gruesome details of how we get this number, but it has to do with essentially measuring the way the material absorbs this light, and you compare it to the way this amount of light gives you light out. You also have to tickle this thing directly to kind of see what this piece does. So that's the stuff that's hiding in there. I just want to show you one thing here. This is data out of a paper that Tracy and I published. So I hope this kind of gives you an idea of what's going on. So I have 2 things here. This dashed line is absorbance. So this is, I just measure how much light gets absorbed. I just want to see what light, I don't care if photons come out or what happens to them. I'm just saying, did it get absorbed? That's the dashed one. The solid one is excitation. So this is the one where light is coming out. So I'm comparing what generates light to what goes in. And you can see with yttrium borate, they pretty much track. So the light that's going in is giving me emission. So this has really good hand-on. This one, not so much. Like at 150, I'm absorbing all this light, but I'm only getting that much out. So I'm losing a bunch of energy here somewhere. And again, this short wavelength stuff is what's going into the host. Out here, I'm hitting it directly. And we need this too, because this kind of tells us what the europium does by itself, which is another piece that we need. but this kind of gives you an idea like, oh, these are pretty much the same, so if I absorb it, I get light out. Here, I'm absorbing all this and nothing's coming out. So then we can use this to measure transfer efficiency, that A to T thing, which is really just the fraction. If I put 100 in here, how many make it over there? Again, it's not that number. That number you can measure. It's the hiding one. How many did that? Because it's parsed between all these things and you can't really separate them. But doing this kind of spectroscopy, we were able to just estimate this piece. And then kind of no matter what's happening here, you can still see this. This might be terrible, but we could show that you're transferring a lot of it and then something bad is happening here. And that's all hiding in the material. But we were able to separate all that stuff out. So what should it look like if we could measure it? Well, it should look like this. So let's just think about this one. So these different curves, let's just look at this bottom one. So this is the transfer efficiency, so it's a percentage, a fraction. And here's concentration. So if there's no dopant, there should be no handoff. There's nothing to hand off to. And then as I add more and more stuff, I expect the transfer to increase, because if I say it's europium, I put a ton of europium in there, I increase my chances of catching the electron. It's going to kind of flatten out. At some point, I'm just going to run out of electrons to grab. But they should kind of go like this. As I increase the concentration, the handoff should get better because there's more of a chance of doing a handoff. And then these are curves that show what happens depending on how good the handoff is. So you use this kinetic expression. This is basically the rate of handoff to the dopant. N is the dopant concentration. This is the rate of handoff to the dopant plus the rate of handoff to anything else bad that can happen. So this is a real simple kinetic model that was actually developed, well, one group that worked on this was a group of colleagues of mine at Sylvania. It should act like this. And actually what we found is we can measure this thing, alpha over beta. And if a bigger alpha over beta means it's better. So if alpha over beta increases, you see, if it's not very good, I increase the concentration, it keeps going up. You have a material like this, you barely increase the concentration, it jumps up to 100, and it's just always 100. So if we could measure such a thing, then we might be able to distinguish between different materials. So I just want to show you one example. I like this example because it looks really good. So this is yttrium borate with samarium in it. It looks just like the cartoon. I see, and we measure this doing that spectroscopy. So we showed that we could do this. And then we kind of started trying to do it on everything. What can we measure? How far can we go? Because what we do is we fit this, actually we fit it to a line. I might have a chance to show you that. We fit this to a line. This obviously isn't the line, I have to change the axes. But we'll fit this data and calculate something like this. Then you say, what, okay, 10 to the minus 21 cubic centimeters. So everyone needs to know that. The units are weird, I won't worry too much about that, but we can do this for a lot of materials though. And then we can compare this and compare between materials. And the goal is to be able to say, okay, why is this one good and why is that one bad? But it starts with being able to get this kind of a measurement. So we did this, it was pretty successful, I think. The first one we did was with Tracy. I showed some of that data. She was the first one to do these measurements. And we published this paper where we measured this in yttrium borate, yttrium oxide. First time I'd seen anyone try to measure something like this. Tracy was in the lab a lot. Tuan is a service chemist at Sylvania. He's the worst golfer ever. Golfing with him was super fun because you literally had no idea what was about to happen. You would usually kind of be like sort of away in the back, like, I don't think you can hit me from here. No, Tracy did some killer work, bunches of work on this. And it was really slow because we had to have to work under vacuum. So we're under vacuum, then you gotta bring it back up to atmosphere, then you gotta put a filter, then you gotta pump it back down, then you gotta measure it again, then you gotta bring it up, and then you change the filter. So after Tracy left, I bought this fancy filtering device. And then yeah, Tracy came to lab and she was just like mad at my other students, like, it's not their fault. Just because they have to do this in like a third of the time that they did. So that was like the first one. This was pretty cool. This was some work Rosa and Katie did. Gadolinium was known to make this material way more efficient. So we were able to do the measurements that showed how this was working. I went to San Antonio and presented some of this stuff. The three of them are all here. I wanted to show pictures from San Antonio, but I thought better of it.
Good idea.
The monkey, what was that play? The monkey something? Anyway, I won't speak more of that. Then we did this beast of a paper. This was Max Wallace. A lot of you know Max. He was some kind of crazy workaholic. He did so much work, and he just tried everything. So we put all kinds of stuff in there. You have to make linear plots, so you take 1/over transfer versus 1/over concentration. You fit these lines, you get alpha beta ratios. We compared it to the energies of these dopants relative to the electronic structure of the host. We made this crazy correlation. We distinguished between hole traps and electron traps. This has to do with the mechanism for how it catches that thing. It can grab the hole first or the electron first. And we found out hole traps are just lousy. Electron traps get better and better depending on how big of a drop this is. So samarium's here, and that's pretty good. Europium's here, that's even better. So this was really cool. That paper was an epic labor of love because it was so much data. We were doing a lot of new stuff. Reviewers, it was kind of funny, these papers, some reviewers would be like, this is super cool. Other reviewers were like, you're not allowed to do that, reject. So it was a bit of, and this was a labor log. This thing got rejected, and me and Max spent a long time mostly rewriting it and explaining ourselves. We didn't really get much more data, and finally published that. I thought this was really cool though, because this was really the first time I had ever seen anyone correlate this trapping efficiency to anything, to have anything on the x-axis. So this was very cool. We did a lot of other stuff with this. We looked at what if we make defects? So my skull and crossbones, what if we put that in there on purpose? What happens to that? Me and Asher and Michaela, who are here today, we published that's the last paper I published, was about putting defects in there on purpose, trying to measure how that happened. A lot of other projects. My last grad student, Barrett, was trying what happens if you put two of these things in there at the same time. What happens is data that is extraordinarily confusing. I'm leaving, obviously, but if I was going to stay, we found a lot of cool stuff, but it's really a lot going on when you just put one more thing in there. So there's a lot of, I wish I could talk about all the stuff, but those are the stories I wanted to tell. One more, which is how can we measure this thing? So how can we figure out how much is going there? Because again, it's hiding. And the models, so the kinetic models say, if I make a big particle small, then the transfer efficiency curve just gets flattened out. And basically, all this energy is getting lost to the surface. So this is the model. All this gets lost to the surface. So if I can measure this curve, we can measure how much goes to the surface. So what Chris and I tried to do was measure this, compare it to this. We did okay. We got data that looks like this. So here's big particles, 500 nanometers. Here's small particles, 120, and we see this kind of this squashing effect. Obviously, something's going on over here because it keeps going down. It's weird the way this works is here's that kinetic model. The way this works is if you have surface loss, you actually multiply it by that. So if this is 1, that's actually good. Surface loss of 1 means multiply this by 1, in other words, same thing. But if I have a lot of surface losses, actually this number gets smaller. And if this is 0.4, it means 60% just got lost to the surface, and the other 40% is going to my stuff. So this was pretty cool, this is tricky. I presented some of this at Materials Research in San Francisco. It was pretty cool. I think people really appreciated what we were trying to do. It's really hard to do. This is pretty ambitious. But Chris and I did publish this paper with another undergrad from physics, in JPhys Chem C, showed how we could kind of measure that part. Then me and Rusty and another undergrad tried this in yttrium oxide, making nanoparticles of yttrium. I got some interesting results. Actually found it wasn't a problem with the surface, it was other things, but that's kind of interesting. Then me and Zach and Max tried this on yttrium phosphate. I made Max present this in Orlando. He was rather not keen on this idea. But I said, hey, there's a materials conference at Solid State, the Electrochemical Society. You should go give a talk about this. And I don't know, most of you remember Max. He did a great job, but my man was nervous. So that's, you know, and like I said, we did a lot of other types of things. I wish I could talk about all the stuff. There's some students in here whose work I didn't talk about at all. But these are some of the cool success stories. So I keep thinking about my career. So this is the part I'm trying to make mom proud now. Here's cool stuff I did. I published a bunch of papers, including some some chemical education papers with some labs, basically. Me and Tony did a really cool lab that was actually really mostly his idea. He's like, we should do this thing where we change the ligand on the transition metal, and this is going to happen. And I was like, dude, let's publish that. That's cool. So we did that. We did some other. Me and Tim published a kinetic one. This is I'm really proud of. It's like $900,000 of money that I brought in from outside. So like a couple NSF grants. National Science Foundation grants are really hard to get. That's like 1 in 4. The first time I got an NSF grant, for real, I was alone. But when I found out, but I pretty much did like a touchdown celebration. Because it's hard to do. I got a couple of those. I got some other research funding. I'm really proud of that. That's hard to do, and especially at a place like Central. What else? Oh, I got to go to lots of conferences, and I want to highlight a few of these invited ones, because that's cool, because that's when you're like sitting at your desk and then someone says, hey, you're famous, come give a talk. So me and Tracy went to Japan for this one. Actually, this is no joke. I've told this story a lot of times, but the guy introduced me. First of all, I'm screaming nervous. It's a huge room. Hundreds of people are in this room. And he introduces me and he says, this is Professor Anthony Diaz from Central Washington University. He's very famous. This is for real what the dude said. And first of all, like, people who cared about blue phosphor, I was famous to them, but most people are like, who is this guy? And then I'm so nervous, like the pointer's doing this. So I just stopped trying to use the pointer because I just couldn't handle it. Went back to Japan, I was invited to this thing. Me and Lindsay went to this one. This was a lot of fun. And this was crazy because people are coming up to me from all over the world and they're asking me about my paper and asking me what I think about stuff. That was very cool. This was 3 days of talks. Lindsay and I almost couldn't hold it together at the end. This guy just kept saying, why? And then he would like show something and then say, why? And like we're kind of punch drunk by then, so I'm trying not to laugh out loud. And then the grand finale, he's like, this is the 3rd time I'm saying why. Like you're doubling down on this why thing. I went to Vancouver with Troy and Max. He's telling a story about how Troy made me shotgun a beer in the hotel room bathroom. Yeah, caribous. Got invited to Atlanta. That's the last time I was on a plane. This was got invited to talk about some of the defect chemistry stuff I was doing with Asher and Michaela. What else did I do? 1 billion students served. This is really cool to me, these 8 degrees. All the faculty here know what a lift this is for the student and for the faculty. This is a lot of work to get a student through a master's degree. And so that I'm especially proud of. And then I was a chair. Yeah. You know,
Took one for the team.
I felt like I was pretty good at it, but this was terrible. You're not going to believe this, but professors are really smart. They're happy to remind you. So, I keep getting this question. This kind of cracks me up. What are you going to do when you retire? People act like they're concerned. I've never been like defined by my job, like right. So like I love my job, but I'm doing it because I get a paycheck. So people will go, oh man, what are you going to do? Whatever the hell I want to do. But I don't want you to worry about me. So I've assembled a montage. One thing I'm going There's more. Oh yeah, I have to babysit these cats. This is Ada. This is really their names, Ada and Epsilon. Yeah, I told Amy I'm going to paint Epsilon's toenails every day now. Let's see, jam with these guys for sure. You should come see us play tonight. Jam with Tim for sure. We're rocking out here, or seriously rocking really hard. There we are at the Red Horse. We're all going to be at the Ridge later today, so at the Rager. So, what else am I doing? Oh yeah, that one again. Oh yeah, for sure, Rocket League. We will kill you. That usually means this is happening. This.
Right on.
I'm not going to explain this one. But my daughter's name is not Quinn Marvel. Absolutely this. I'm so lucky. Okay, I'm almost losing it. I'm okay. I'm hanging on. This is pretty much what I'm doing. Okay, so there's a lot of people I want to thank. I'm going to hold it together now. This is, I really feel really lucky.